Welcome back. Let's finish off our dynamic array. So we've got two remaining goals. One is to implement a safe getter function, and then it's to implement a cleanup function that frees up memory. So why do we need a getter? Why can't we just access it like so? You take the array and you just access the property at index I, right? The reason why is that if this I is a negative number, what does it return? It returns something that you don't know what it is. It's certainly not part of the memory that has been allocated for your array. And if the capacity we left off last video, the capacity now is 20 because the initial capacity was 10. We reached the 11th thing to push into the array, and so we doubled the capacity here. What if at capacity 20 you go in and access the index at 21? Well, it's going to be chaotic as well. And then also, what about if the capacity is 20, you've got 12 items as we have here, and you try to access the 13th item. So I equals 12. And because arrays start at 0, you're looking for the 13th item. Well, it's memory that's been given to your array, but it hasn't been written, so you don't know what's in there. And I don't know, it could cause a lot of problems depending on whatever it comes back with. It can, I guess, destroy your program because it's gibberish. So that's why we need a safe getter function. And basically, this function just needs to give you back the result if the index is actually in the data. So the first thing we're going to do, let's create our getter function. So we know that we're pushing in integers, right? We know the type is an integer of the actual data when it comes back. So let's start off with returning an integer. Now there's going to be an issue here, but we'll get to that later. So let's just call it get. It takes in our array, but it's a pointer. And we do this because of reasons explained in past videos. Basically, this function gets a stack frame that gets wiped. And so any copies you put in here that's not linked to an actual thing that exists outside gets lost. Okay, so, and then we need the index, which is an integer. And then basically we want to check the upper and lower bounds, right? So let's go int upper bound. So what is the upper bound of our array? Well, it's array length -1. And that's because, as we said, arrays start at 0. So your 11th object is 10 on the index, if that makes sense. Because it starts at 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is your 11th object. So that's the upper bound. That's the most high index that's going to be valid. Let's create a lower bound here, which is, of course, 0. And then a simple if function, right? So if the index supplied is less than the lower bound, it's not valid. Or the index is greater than the upper bound, it's also not valid. But what do we return here? If it's not valid, we have to return something. And we can't return a null if it's just an integer type of return. So what do we do? Because null is not a legit integer. So there's two ways that we can approach this. One is to accept another property in the function, as I got my notes up here. So if we return a status code, it would be an integer status code. A pointer can be null. So, oh, sorry, yeah. If the status code is 0 or 1, Wait a second. No. It has to be an integer. It has to be a pointer. Otherwise, it gets lost in here. So the pointer has to contain a status code, like it's a pointer to a memory address that contains a status code of 0 or 1, and thereby we can report the status, whether it's safe or not safe, whether we've given an invalid or a valid index, or we can just return type of pointer to an integer. So if we do that, a pointer return type can be null, just as in the same way that realloc and malloc we check for null. And malloc has a return type of a void pointer, a pointer to anything. So a pointer can be null, including a pointer to type integer. So let's do that. Now, what does this mean in terms of calling this function, right? We now need to destructure. Is that the word? Destructure? We need to dereference, I guess, the result to actually get the result if it's not null. So, sorry, I don't know if I explained that super well, but let's just keep going. Okay, so if it's invalid, we actually return a null here. And then otherwise, if it is valid, we'll return the array data at index. But because we are returning a pointer, we have to use the address like so, using the AND signal. Then in order to get the index, so let's get rid of these guys. We will still print the array contents, but let's just get an index. Let's get one valid index and one invalid index, right? Valid index, getting index 7, then we'll line break. So the get is going to give us a result. It's going to return something of a pointer. So let's go integer pointer result equals a get of using the address of the array and getting index 7. Here we've pushed 12, so we know index 7 is valid. So we would expect an answer. But let's check if the whole point of having the result potentially be null is we need to check it, right? So if result is null, much like the same as we checked the other things that could be null, like malloc, realloc. So if result is null, we will printf invalid index supplied, could not get, line break. Else, let's print the result, which is an integer, so it's %d, line break, and the placeholder is the result, but we need this because the result is a pointer. Okay, let's try that first. So gcc-w all-w extra, output will be, let's say din array valid get, and we're going to use our dynamic array.c. And now let's run it. Din array valid get. Sweet. So valid index, getting index 7, we get a value of 6. And we can confirm that because our array has these values. The first value, second, third, fourth, fifth, sixth, seventh. The 7th item is 5. But because it starts at 0, getting index 7 is actually asking for the 6th item. So first, second, third, fourth, fifth, sixth at index 7, and it's giving us the value of 6. So the valid index is working. Now let's do an invalid index. All right, so invalid index, getting index, let's say 25. Yeah, 25 is not valid. So in the same way, we dereference the result. We put the return of the get into this result variable. So we pass it the address of the array, and index would be 25. What's wrong here? Blah, blah, blah. Oh, yes. We've already used result in a previous line, and so we're just going to use result 2. We'll maybe have a chat about the weaknesses of C. Being such an early language, it just, there are some things that modern languages do, which mean that you don't have to keep putting the onus on the caller to get its variables right, and every time you call get, having to do a new variable. C basically just doesn't have the object-oriented, or doesn't have really the ability to put the getter function on the struct. And so we have to call this in sort of like, I guess, a primitive way, but it depends on how you look at it. Anyway, result 2 is getting index 25. If result 2 is null, we will just copy paste this, printf could not get, else we will print this and use result 2. So this is this is something, if I just pasted it, it'll print result, but that's the first result, right? And so that's something that modern languages have tried to alleviate by putting functions as recallable on the definition of an array, in this case. But we're learning how things work under the hood. So those languages eventually compile back down to C, most of them anyway. Cool. Let's test this out. Let's go up and let's go invalid get. And run it. So the first get returns a 6, which is correct, and then we're getting index 25. It says invalid index supplied, could not get. So it's actually hit our error path here. Excellent. The next goal is to implement a cleanup function.